to finish. I hope there's only 4 exercises, so I think if I write down all the solution and then, yeah. So let's consider a multiple regression model, y x beta equal plus epsilon. We have the epsilon following normal distribution, mean 0, and then a sigma multiplied by identity. So using the distribution of beta hat, we show that this following chi-square. So I'm assuming this is derived during the lecture. And I think the additional question is that we're now going to use this distribution of beta hat to find a non-central chi-square distribution. So I'm assuming this is already done in the lecture by using the distribution of beta hat to get the chi-square distribution. And now the question is that using the same distribution of beta hat and then find a non-central chi-square. So that will be the kind of like the new problem here. Okay, so I think, so I'm not sure if you, or maybe I forget that I think in the first homework, we already showed that beta hat is the equal, or is following a normal distribution with mean beta. Here I'm just going to use the same notation as in the homework, which is k by 1 multiplied by 1. So k is the number of features and 1 is the additional intercept. And then we have the variance of a sigma x transpose x inverse. So I'm assuming this is known to us. I think we already did this in homework 1, right? Yeah. So now we are interested in the we're going to use the distribution of beta hat to find a non-central chi-square. Let's see. Yeah, so non-central chi-square. So that means we also need some non-central parameter here. So we need to define the things here to define our chi-square distribution. Okay, so is there any question regarding this one, the normal distribution for beta hat? Okay, just a brief summary. Beta hat is defined as a linear transformation of y, and y is also a normal distribution, and then its distribution is coming from epsilon, so that we have this equal to normal distribution, and then you can derive the expectation and variance to get these two terms. Okay, that's just a high-level summary from homework 1. Okay, so now we're going to define a matrix V in the following way. We're going to define as x transpose x raised to the power of 1/2 multiplied by our beta estimator, and then over sigma squared. If you want, you can also write sigma squared. Here, we don't need the square, just one copy of that. Yeah, so you can also write sigma inverse in the front if you want, instead of the fraction form. Okay, so we're going to define the formulation in this way. And now, maybe I can ask the question here. What would be the mean? Or first of all, y is also a normal distribution for our new v here that we define here. Y is also a normal. Because it's also it's essentially also a linear transformation of y, so that all the derivation or the conclusion that you get from beta hat also carry over to v. So that's why it's also a normal distribution. And next, the question is that what will be your mean vector and the variance here? Okay. Yeah, so you can perform or you can evaluate the expectation of v, and then by plugging in this term here, and then with the same simplification, you will get this is x transpose x raised to the power of 1/2, and then the true beta value, and then over sigma. So is there any question regarding this? Yeah, here I'm just directly writing down like a solution. But is there any question regarding why is taking this form here? So one way you can do is that you just plug in this term here, and then whatever or the part that I'm marking here is considered as a constant. So you can move it outside to the expectation, and then this problem will reduce to the problem of finding the expectation of beta hat. And then essentially it's just this coefficient multiplied by the true beta value. And next the question is, what is the variance of V here? So one way you can do is that, again, plug in the terms that we define here. This is 1/2 and then beta hat. You will also get the sigma -2 and then x transpose x 1/2 variance of beta hat, and then x transpose x inverse 1/2. And then this will just coming from the same derivation as your homework 1. And then actually, if you simplify this, you'll get an identity matrix. So now another question, just what will be the dimension for this identity matrix? It will be the same as your or actually, if you can plug in the k, here I'm just write p equal to k plus 1. So p by n, n by p, and then p by 1. Okay, so you will still have the same as the dimension should be same as your estimator. So this should be a p by p, or k plus 1 by k plus 1. Okay, so here I jump a few steps, or without talking about too much detail on this one, but the same derivation is coming from your homework 1. But the bottom line, but the final result up to this point is that our V, the one that we define in this way, has a normal distribution with this particular mean vector and this particular variance covariance matrix. Okay, and the reason why we want to construct this V, and also by finding its mean vector and the covariance matrix, is that we want to answer the question from the homework to define a non-central chi-square distribution. So the non-central chi-square distribution can be defined by V transpose V. I think this is also what you've done in the homework, not in the lecture. Did the non-central chi-square, the central chi-square, is it derived in the lecture?
Yeah.
Yeah. So do you still remember what is the difference between this approach and deriving to the as the non-central chi-square, the central chi-square? Is that you need to multiply by something here to center the mean vector here. So without doing that, you basically do not centering to the zero of the normal distribution. So without centering the normal distribution, and then the chi-square distribution that you develop, that is a non-central chi-square distribution. So if you center to the zero for your normal distribution, then the chi-square distribution that you derive is going to be a central chi-square. But here we do not center the normal distribution for V. Then the chi-square distribution that we are going to derive is going to be a non-central chi-square. So that will be the difference. Okay. Yeah, so this V transpose V is going to follow a chi-square distribution, dimension k plus 1, degree of freedom k plus 1, with the central parameter of this term here. Maybe I can write a brief notes here. So for random variable v, y, that follow a normal distribution dimension n with a particular mean vector. So this is not going to be a 0. So we are not going to center around to 0, but with identity matrix, covariant matrix. And then v transpose v will follow a chi-square distribution, degree of freedom n, and then with the non-central parameter mu transpose mu. Okay, so here just a notes. And this is what I referring earlier, that we are not centered around. So this is not going to be 0. And then if you perform this transformation, the chi-square distribution that you derive is going to be a non-central chi-square. So in contrast to what the professor showed in the lecture is that when you center around to make this mu here equal to 0, and then the chi-square distribution that you derive is going to be a centered chi-square. So without this parameter anymore. So that would be the key difference. I'm not sure if that makes sense or... Okay, good. Yeah. So following that, we have the mu transpose mu. So that in our case, the mu is this vector. So we will have... Okay, so I have a typo here. There's no square at the moment. Yeah, so when you take the y transpose y, which is the mu transpose mu, then here you have a sigma, I'm going to write it as a product, and then beta transpose x transpose x, and then beta. So that will be the chi-square distribution. And here we're just going to need to specify explicitly for what is v transpose v, which is beta hat x transpose x, and then beta hat over sigma square. And this follow, I'll just put this chi-square distribution. Okay. There's a hat, there are two transpose here. Yeah, so this term here following a non-central chi-square, and then with a non-central parameter defined here. Okay, so is there any question or comments? Okay, next, exercise 2. Yeah, so here the only difference is that we have this assumption here. So instead of a sigma multiplied by identity, here we have sigma multiplied by another matrix V. And this matrix V should be dimension, what is the dimension of the V? It should be matching to your data point, right? So it should be n by n matrix. Yeah. So the identity in this simple, or in this version, should also be a dimension n by n. And here we just have an additional, instead of using the identity matrix, we have another matrix V. And this should also having an n by n dimension. Yeah. So that's the only difference. Yeah. So under this new specification, with this additional matrix multiplying here, and then we are interested in the linear, this beta estimator formulated in this form. So now you can see that when we introduce matrix V in our setting, our estimator for beta also is a form or a function that involving V here. Yeah. So I think, yeah, in midterm exams, we show that this is equal to that. So our question here is that to find the distribution of beta G and then formulate it in this way. And the reason for that is that we introduce the matrix V in our setting. And then that gives us the formulation for beta G also involving V. Okay. Okay, so yeah, maybe let me write down the beta G here as X transpose V inverse X altogether inverse X transpose V inverse Y. Okay, so this is our new estimator for covariance, the variance of epsilon equal to that. So in this setting, our linear estimator, our estimator for the linear model, now take the form of this one. Okay. So that will be the setting here. Okay. So now there are a few questions we can ask. What is the distribution for beta g, g hat? So what should we write about the distribution here?
It's normal.
Why is that?
It's a linear transformation of y.
Yep. Okay. So that's the first things we can observe. So it's a linear transformation of y, so that it also inherit the normal distribution. Okay. Now, two more questions we can ask. What is the mean and the covariance matrix here? What are some approach that we can solve for these two items? We can still find it by plugging in our formulation for beta g and the expectation of beta and the variance, right? And then by filling in these two components. Okay. So here maybe I'm just going to write down the answer, and then if you want, you can try on your own and then see if it's going to match. Yeah. So the expected value for this beta hat g is still going to be the true value, the true beta. So all you need to do is just to plug in this form and then calculating the expectation. And here, both v and the x are considered as constant. So you can move it outside the expectation when you want to work it on your own. Yeah. And then the variance for beta hat, for this beta hat g, is that x transpose v inverse x altogether inverse. Okay. So I think earlier, without the new v, what we get is that the covariance having this form here. When we adding this new condition in our covariance matrix for the epsilon term, the variance for the beta g are now different, involving a v as well. Okay, so if you want, just plug in your estimator in this formulation to the variance and then simplify. But here I'm just going to write down the answer for now. Any question regarding the high-level idea here? Any question or comments? Okay, so that's that. So under this new condition here, and then we find that in exam or in midterm, we find that the closed form solution is going to be that. And then we also answer the question for the distribution of beta g, which is a normal that's getting from the distribution for y. And then if you evaluate the expectation and variance, you will get the corresponding mean vector and the covariance matrix. Okay, so now for B and C, find a central chi-square and then find a non-central chi-square originated from the distribution that we derive in here. Okay, so using the distribution for beta g, we need to find a chi-square distribution, a non-central version, and then so maybe first let's work on the central version, and then a non-central version, chi-square, and then you will need to define your non-central parameter here. So this is part B, and then this is part C. Okay. So any idea or comments on how we can perform or answering part B and part C? So actually, it's just similar to the first question. So we need to perform some kind of a transformation here by multiplying the beta g with some, say, some combination of the terms here. And then we're using this rules. If a y follow a normal and then y transpose y follow a chi-square, either a central version or non-central version. So that would be the high-level idea here. Okay. Except that instead of a beta hat, now we are working with beta hat g, or beta g hat. Yeah. Okay. So that will be the high-level idea. And now we're going to look into the details. Okay, so we are going to define, so this is for the central version. Let's define a v in the following way. Let me write this too ugly. Inverse, and that multiply by 1/2, and then beta hat g. So here we are going to minus or subtract the beta g, subtract this beta true value from beta g hat. So this is when we are going to like set some other distribute from a normal distribution that center around beta. When you minus the beta, so here I'm assuming that it's greater than 0, and then you will center around that. When you subtract the same terms, you're basically moving the entire mass for the normal distribution to the 0 mean vector. So we are shifting the normal distribution by doing this operation, and then scaling the factor to standardize it, the variance term in this normal distribution. So that will be the overall idea why we are going to define the v in the following way. The subtraction is that we're going to center into the normal distribution to 0, and then scaling the variance covariance term. So that would be the high-level idea. Okay, so after we do that, this kind of transformation, we found that the v here should be centered around 0 and then sigma square identity. Okay, yeah. So any question regarding the high-level idea? So maybe I can elaborate a little bit here regarding why, when you do this kind of transformation, you will end up with a 0 mean vector and the identity, or the usually people call this isotropic, but just sigma square multiplied by identity. Okay, so yeah, again, starting from our beta g hat in this form that you can get from the expectation and the variance. So now we are going to, so the question that we are going to answer here is that why this is, after this transformation, it reduced to 0 and this sigma identity. So we're going to evaluate this V matrix, this V here, explicitly. So maybe let's use square bracket for this. Okay, so this term here, they are all non-random, right? So they can move it outside to the expectation. X transpose V inverse, and then X. Okay, 1/2. Now we have the expected xg minus beta. Okay, again, this is also a constant terms here. So essentially we can also, so the expectation is only going to affect your estimator here. So now we just need to evaluate the expectation of beta g. And here we can use the information that we get from here. So the expected value of beta g hat is equal to beta. So as you can see, this is going to be 0. Yeah. So that's the reason why we need this kind of a transformation. When we subtract the beta, so as you can see, when we subtract the beta here, when we write everything explicitly, you will see that in the end, you will end up with the 0 vector. So that's what I also meant earlier by shifting the center mass of a normal distribution towards 0, and then you will get a centered normal distribution. And similarly, you can also evaluate the variance of this. X transpose V inverse X 1/2, and then beta G hat, beta G. Okay, so now you just need to perform the similar operation as what we did before. So we have X transpose V inverse X 1/2, and then variance of this thing here. And here I'm going to comment that because the beta is a true value or is a constant, so when you subtract a random variable by a constant, it does not affect its variance. So the variance of this difference is essentially the variance of beta G only. So that would be one comment that we can make here. And then you have X transpose V inverse X, and then 1/2. And then you can plug in the variance of beta G hat from here. So this, let me just copy it down here. This is sigma square X transpose V inverse X. And this is inverse, okay. Yeah, so as you can see that you have 1/2 copy of this and then 1/2 of copy on the right hand side. And then you have -1 or 1 copy in the middle. So in the end, this will reduce to sigma identity. Okay, so yeah, here I'm just commenting on why when we write the V in this formulation, and then this V will follow a 0 mean vector and a sigma identity. Okay, let me ask a follow-up question. What is the dimension for I here? Actually, I also don't know, but let's take a look. Let's evaluate. So we have the variance of V. Maybe we can evaluate from here. Okay, so I will write P by N, N by N, and then N by P. This is a P by 1. Okay, so in the end, you will have P by P multiplied by P by 1. So okay, back to the notation, K by 1. Yeah, so indeed, K by 1. Yeah. So this transformation do not alter the dimension, but it's centered to 0 mean vector, and then with this particular covariance variance matrix. Okay, so now after all the details, let's move back to the question. We want to find a part B, just a central version. Okay, so after we define the V here, and then this V transpose V should have a chi-square distribution, and then what is the degree of freedom here? Should be the dimension of the distribution that we found, or that I asked earlier, right? So there should be degree of freedom K plus 1. Okay, so I think that should conclude part B. So find a central version chi-square originated from beta G. Okay, any question up to this point? So K plus 1, or maybe you can also write V and V transpose V more explicitly as beta G minus beta X transpose V inverse X beta G minus beta, and here's the sigma square. So our V is defined with this operation, and then if you write everything explicitly, and this one follow the chi-square distribution K plus 1.
Was the first
beta have G minus beta transpose.
Perfect, yes. Nice. Yeah. What is the dimension for this thing here? Just let me ask a follow-up question.
Is it a scalar?
Yes, should be a scalar, right? Yeah. Because chi-square is a univariate distribution. Here we talking all the normal distribution is a multivariate normal. So after this transformation, you can, if you want, you can write this. So this will be 1 by p and then something p by p and then p by 1 in the end. So in the end, you should have a scalar. So this should be a univariate distribution. Yeah. Okay, so this is a central version. Let's talk about a non-central version. So again, the non-central version, the high-level idea should be similar to what we did as in exercise 1. We just don't need to center or to standardize the mass by subtracting the beta value. That's the only, or that's the thing we need to do to create a non-central version. So yeah, actually we can borrow from here. So the only thing we don't need to do is that subtract beta. Okay. I think I see. No wonder. There's a typo in the solution. Did he post the solution after every homework? Right, okay. Sometimes the solution, there's a typo. So I think I found one typo here. There should be a sigma inverse. Yeah, this is not, so when you look at the solution from after you submit the homework, just notice there's a sigma inverse here. This is similar as what we get here. So all the transformation, you need to standardize it, the variance. So that's why you need a sigma inverse there. So that's what is missing in the solution. No wonder, okay. Yeah. Back to question C, we want a non-central version. So the only difference, again, is that we don't need to minus the beta to center the mass of the normal distribution. So we are going to define the transformation in this way. So the only difference from part C to part B is that we are not subtracting this one here. But we still need to perform the same standardization. So in the end, you will have the same sigma squared multiplied by identity. But we won't be able to get the center, the mean vector into 0. Okay, so here, maybe let me just write down the solution here. So this V here is going to follow a normal, and then with non-centered mean here. So the mean should be x multiplied by V and then x inverse. And then one copy of that, and then the true beta vector. But we have a okay, I think there's another typo here. Let me think about it. I see. So if you evaluating this form without the sigma inverse, then you will end up with a sigma square identity. But what we want is that a V that following a normal of a mean and the identity only. So that's why you need to multiply a sigma inverse in the front. So if you don't have sigma inverse in the front, then you will have the sigma square identity. Yeah. So that's just based on how you set up the question. But in the end, what we want is this one, the centered to zero normality with a identity covariance matrix. But if you don't multiply the sigma inverse in the front, then you will end up with a sigma identity. Then the V transpose V will not be equal to the chi-square, because chi-square is essentially defined as n copy of a standard normal, and this will be a chi-square degree of freedom n here. But this Z, I, will need to follow a normal with a 0 and then 1 here. Yeah. So don't forget, so just based on your, kind of like based on your preference, you want to multiply the sigma inverse in the front, and then you will have the sigma inverse when you evaluate the variance. But what we want is that we don't want the sigma square here when we construct the chi-square. Yeah. So that will be the only details here. Yeah. I'm not sure if that makes sense or if it is confusing.
Can't you just divide by sigma squared after? Like instead of V prime V is chi-square, you just do, like, I guess this form with V prime V over sigma squared follows chi-squared.
Yeah, I think you can divide it in the end because it's just a constant term. Yeah. Yeah, but yeah, so it's based on your your preference of operation. Yeah. So if you don't involve in here, then just make sure that you divide it in the end. Yeah, to get the sigma identity, not the sigma not the sigma square identity, to get the identity only. Yeah. Because when you construct the chi-square, you need a 1 here, not sigma square here. Yeah. So you need to standardize it in terms of to get the identity in the end. So that would be the bottom line. Yeah. Okay. So back to part C. So yeah, so here we put the sigma inverse when we construct the V here, then the V, the resulting V should have an identity matrix here instead of a sigma identity. Okay, so that's the only difference. And then the V transpose V here is going to be a chi-square. Degree of freedom should be the same dimension here. So it should still be k plus 1. Yeah, degree of freedom k plus 1. And then your centered parameter should be beta transpose x v inverse x inverse beta over sigma squared. Okay. Yeah, so just to summarize the difference between part B and part C, or maybe I can also, starting from part A. So here, part A, okay. So just to summarize or to bridge the connection between A, B, and C, is that in this new setting, for our linear model y equal to x beta plus epsilon. So instead of this is the sigma squared multiplied by identity, we are now investigating this linear model in the specification that the covariance or variance matrix of epsilon is sigma squared multiplied by V. So that's the first difference in the setting. And then this is what you get from the exam, that you find that the solution for the coefficient of the linear model under this new specification having this form. So without that form, which is just the x transpose x inverse x transpose y, that's for the specification of sigma identity. But under this new specification, you get the linear coefficient in this formulation. And the part A is asking the distribution for that. So to answer the distribution, we first comment that this is going to be a normal distribution, and then we comment on the mean vector and the covariance matrix. You can calculate them by calculating the expected and the variance. Okay, so that's part A. And then to bridge B and C with part A is that part B is we ask for a central chi-square, and part C is that we ask for a non-central version. Okay, so that means we need two kind of transformation. So to get the central version chi-square, the transformation that we do is that this one. So the high-level idea or the reason why the V should be written in this way is that, first of all, we need to center the beta G to by subtracting beta from my beta G hat. So that we basically move the center mass towards 0. And also mathematically, you can see that in the end, you will end up with 0. So you need to center around. And then you also need to multiply by this to standardize the covariance matrix, to end up with an identity covariance matrix. So under this transformation, you will get your V here. And then the V transpose V will result in a chi-square distribution. And this is the central version. As what we defined earlier, that we center to 0 by subtracting the beta. And the part C is that we want to get a non-central version. So the only difference is that in this transformation, we do not minus a beta here. So that's what we don't want to do here. So we do not center toward zeros, but we still have the same operation to standardize the covariance matrix. So we still end up with an identical covariance matrix, but this mu here is not going to be a 0. Okay. And then in the end, the V transpose V will end up with a non-central chi-square with a non-central parameter. I'm not sure if, based on your preference, and then what do you want to call this thing? And then with this non-central parameter in this form. Okay, so that would be the overall idea. Okay. I think we only have 5 minutes, so we won't be able to finish all of them. Okay. So, so for the remaining 3 questions, what do you want to talk about? The exercise 3 and 4. Maybe let's comment on exercise D then. Okay. So yeah, we want to show that G, so this is E here, not epsilon anymore. So E is the residual, which is the true value minus the predicted value. And here is the predicted value, so it's x beta hat. We want to show that these two terms are independent. And then we're going to show in the following way. So E of G is that y minus x beta G hat. We are going to write y minus x and then x transpose V inverse x transpose V inverse y. So here I'm just plugging the beta G. And then you can write it as identity minus x and then x transpose V inverse x transpose V. Okay, and then all together, so multiply by y. Define that as A. Okay. Then x beta G. So this is the y hat G. So we want to show that these two are independent. Are they independent or not? Okay. So we're going to write that by plugging x transpose V inverse x. Inverse x transpose V inverse y. And let's group this part as B. So this is just B multiplied by y. Okay, so we write E of G as A multiplied by Y and this as B multiplied by Y. What we are interested or what we want to evaluate is the covariance of E hat G and the Y hat G. Ends up with the covariance of AY and then BY. This is equal to A multiplied by the variance of Y multiplied by B transpose. So the rest is just plug in the A and B. So A is I minus, okay. So X transpose V inverse X transpose V. Okay. Covariance of V. Okay, so let's see what under which. Okay, so here, because we're talking about the beta G, so the covariance of the Y's should be sigma V. So this should be a sigma multiplied by V. So this is the covariance or the variance matrix for Y. Okay, so maybe we can comment on that. So Y is X beta, should be still beta true, and then sigma V here. Okay, so B transpose. B transpose is this one here. So this should be, so basically we're just reversing the order and then transpose every terms. So V inverse transpose, X transpose, and then this entire thing transpose. But this is a symmetric matrix, so it still stays the same, and then X transpose. Okay, so now let's evaluate or simplify this term. We should have sigma square in the front. And then these two cancel out. Okay. And then we should have X transpose V inverse, X inverse X transpose. So it's just this thing multiplied by identity. And then here we have a right multiplication. So this thing multiplied by this thing here on the right hand side. So we first need to copy down this part. X transpose V inverse X inverse. Let me know if you see any typos. And then copying this part here. X and then X transpose V inverse X transpose. Closing that. Okay, so I think now it should be obvious. So we just have sigma and then X transpose V inverse X transpose minus. Okay, so now we just need to evaluate this. So you can see that this is essentially an identity copy of this. So in the end, we should have this V inverse X inverse and then the X transpose in the end. Okay, should be 0. Okay, covariance of that equal to 0, so they are independent. So conclusion, EG hat independent of YG hat. Okay, I'll just, oh, okay, we have 1 more minute. Okay, anything, any questions so that, yeah, for the details, maybe you can revisit the video and then if you do not have any question. But any last minute question?
Does covariance equal to 0 always apply independence?
Yes. So you can also think of this. So you have terms. So for example, this is sigma identity, but the rest they are all zeros, right? So that means your ij. So for any ij that is not equal to j, they are 0, so that they are independent. Yeah. So only the diagonal elements, they are the variance term. For the remaining, they are all referring to the ij covariance. So when they are 0, and then they are independent. Yeah. Any other question or comments? Yeah.
Can we also ask you to, for the project, to review our work in progress project?
Yeah, sure. But just let me know the information about the project. I don't have any prior knowledge. So when you show me, maybe give me some background knowledge or something. Yeah.